Canada originally, so I guess there are some shared cultural references. I like this quote from the Canadian hockey player Wayne Gretzky: "A good player plays where the puck is. A great player plays where the puck is going to be." And I think this really captures our eternal desire to look into the future, to see what's coming around the corner so that we can position ourselves better for it. On the other hand, there is also this quote attributed to Yogi Berra, a baseball player: "Prediction is very difficult, especially about the future." So one of the things I want to talk about is the limits of prediction. And I'll start off with 3 examples from different areas. So the first one has to do with weather or climate forecasting. A bit over 30 years ago, they had the first conference to assess the effect of what would happen if the CO2 levels in the atmosphere doubled. And back then, there were only 2 models, and the first one gave an answer of 2 degrees, the second one gave an answer of 4 degrees. And so they split the difference and added a fudge factor, and they came up with this range of 1.5 to 4.5 degrees centigrade. So the strange thing is that, in the last 3 decades, this uncertainty hasn't got any smaller. And in fact, some model sensitivity studies suggest that it's actually bigger. So this is rather weird. Why is it that, with computers so much better technology, this uncertainty hasn't got smaller? And not to mention the increased evidence that the climate actually is changing as we're watching. Perhaps the most graphic example of our difficulties in predicting the future was the recent financial crisis, which was not widely predicted. And then finally, the area that I work a lot in now, biology. A bit over 10 years ago, the Human Genome Project gave us access to the Book of Life, but it's turned out to be a bit of a puzzler. It's still very hard to figure out what the effect of a drug will be. The cost of developing successful drugs is actually soared to over $1 billion. And we still can't predict the spread of pandemics like avian flu or swine flu. So this is all rather frustrating for a mathematical modeler. And what's going on? Are these problems related? Well, I think they are. And I think they're connected with our worldview, our way of thinking about the future. So what I'm going to do is give a very brief history of how we make predictions, and historically and in these different areas. So the first people to build mathematical models for predictive purposes were the ancient Greeks. They developed predictive models of the cosmos, and these were used primarily for astrology. And these models were based on 2 very important assumptions. Both of them were wrong, but that didn't really matter. The first was that everything moved around the Earth. And the second was that everything moved in circles. And this is, circles were, the reason they were chosen was they were considered the most stable and symmetric of forms. And one of the themes of this conference is science and art. And actually, aesthetics has played a very important role in predictive models as well. So this circle-based model worked okay for things like the sun and the moon, which just went around the Earth. But planets appear to follow a more complicated path where they're going to reverse and then keep going. And so to model that required the use of epicycles, circles moving around larger circles. And so then the final model by Ptolemy, it was very successful. It became the official model of the church. It remained unquestioned right up until the Renaissance. So why did it last for such a long time? Well, the reason was that it could predict things, right? It could predict stuff like this, lunar eclipses, to a very high degree of accuracy. And, in a time when it was believed that affairs here on Earth were ruled by what was going on in the cosmos, this was an astonishing demonstration of the power of mathematics. So then, eventually, the Greek circle model finally got replaced when Isaac Newton came along. He combined Kepler's theory of planetary motion, Galileo's study of falling objects, and he came up with his law of gravity, which replaced circles with equations. And Newton believed that matter was made up of solid, massy, hard particles governed by physical laws, i.e. atoms. And this laid out a program which scientists continue to follow until the present day. So to understand a system, you just break it down into its separate components. You figure out the physical laws that supposedly rule each of these components, express as mathematical equations, and solve. And that's what we do in these different areas, such as weather, economics, or health. But how's it actually working? Well, in numerical weather forecasting, it really got going after the Second World War in the 1950s with the development of computers, such as ENIAC here. And soon researchers were producing these big 3D general circulation models of the atmosphere, which were based on the equations of fluid flow. Much of this research was actually funded by the military in the hope of predicting and even possibly controlling the weather. But as we know, while weather forecasting has certainly improved a great deal, it's still far from perfect. And this is despite there being huge advances in computing. I mean, supercomputers today are like 1,000,000 times faster than the ENIAC computer. Observational power, such as weather satellites, huge demand. Forecasting hasn't improved as much as anticipated. So predictions are good for a few days, but things like precipitation, very hard to predict. Extreme events, such as storms. And, of course, controlling the weather seems to be right out. So why is it that forecasts haven't improved more? Well, in the 1960s, the butterfly effect became a popular explanation for the inaccuracy of weather forecasts. So this is the idea that if you get a small disturbance on one side of the world, it kind of ripples through chaos and creates a storm. But I always thought this was a very strange theory, actually, because when you think about it, if you flap your hand in front of your face, you don't get the feeling that there's some sort of exponential force rippling out from you, which is going to change the world. And I think there's actually a much simpler explanation for this. Perhaps not as nice, but it's just model error, right? Which is, when you try to model a complex system like the atmosphere, there are at least two major problems. The first is emergent properties. So local effects in complex systems lead to emergent properties that, by definition, cannot be reduced to simple physical laws. So an example for this is clouds, and these are formed when water droplets locally cluster around small particles in the air, such as dust or salt. So there is no law or equation for a cloud, right? These equations of fluid flow they break down under those circumstances, and all you can do is approximate it very roughly. Secondly, complex systems are dominated by nesting and opposing positive and negative feedback loops. So as an example of feedback loops for clouds again, heat increases water vapor, which increases cloud cover, and this cools the atmosphere, so that's negative feedback on heat, except at night when it does the opposite and heats the atmosphere, which is positive feedback. So these forces are in a delicate balance, which makes models sensitive to small changes. And you see similar problems when you're modeling and predicting other kinds of complex systems. So for example, in biological systems, you have positive feedback, which allows for rapid response, negative feedback, which provides control coupled together. In the stock market, you have momentum buyers versus value investors. So this, I think Heraclitus, the Greek philosopher, put it best when he talked about this harmony of opposite tensions, right? So that the apparent stability is actually a truce between strong opposing forces, which means that the situation can change suddenly as in earthquakes or financial crashes.